I see. Okay. Okay. Can you hear me now, Fran? Sorry.
Let us know if you can't hear now and we're running.
Yeah. Okay. So yeah, so for a long time, this was a big challenge because 70% of the planet was very hard to access. But there's, in recent decades, there's been a shift in thinking about this, where oceans, instead of just being hard to observe areas, if we instead think of them as areas covered by electromagnetically conductive fluid, then they actually can be an area that we can use to probe into the Earth or study our oceans. So salt-watered oceans are electrically conductive because of the salt ions, pretty much. Like you have the heavier positive ions and then electrons traveling in the ocean. And the way that I'll break down this talk is by looking at different types of ocean flow, and I'm sort of organizing them here by the period of the flow we're looking at. So on the shortest end of the spectrum are tsunamis that have periods in the range of minutes. And then on the opposite side is circulation, where that can have periods of like centuries. And I'm going to start actually in the middle with tides, because the magnetic fields from ocean tides are like the marine magnetic field that's been like studied the longest.
So right away, sorry, I wanted to interrupt. So do you need the salt conductivity? So could you not do this for a big lake?
Correct. So that is a common question. Like you would have a much harder time doing this with the Great Lakes, for instance. I do not know if people have studied like the Salt Lake in Utah. But yeah, and then I think there's some seas that like also are kind of close that work because they're salty. Cool. So yeah, so tides will be the starting point. And part of the motivation for tides is also the like recent satellite magnetometer missions we've had. So since pretty much 1999, Earth has had near continuous coverage of high resolution, low Earth orbit satellite magnetometer data. We've had like the CHAMP mission from 2000 to 2010, led by Germany, SOC-C, Ørsted, and then most recently, what I have in the picture here is the SWARM mission by ESA. And this mission has these two satellites flying as a pair, and then a third satellite flying higher. So there's just been a lot of excitement of, can we use all the satellite data to pull out magnetic signals that are actually from the ocean, as opposed to all other aspects of Earth's magnetic system, and can we use those? So this is a cartoon of Earth's magnetic system. And the main challenge in studying oceanic magnetic fields is just being sure that you're isolating those magnetic signals when you're collecting magnetic field data. So the dominant signals, whenever you're collecting magnetometer data at Earth, comes from the fluid core, the outer core. And this can be a signal of like 60,000 nanoteslas, depending on where you're collecting this data. And then our next biggest contributor is generally the magnetosphere. And so if we're at low Earth orbit, those magnetic fields might be about 60 nanoteslas in strength. So you can see we've dropped down like 3 orders of magnitude. And from there, we go on to the ionosphere, which could be maybe like dozens of nanoteslas. And then different places on Earth, the crustal fields can also be magnetized quite strongly, up to maybe 20 nanoteslas. And then the bottom of the list, we get the ocean's magnetic field, which at satellite height is going to be up to 2 nanoteslas. So this becomes, a complete needle in the geomagnetic haystack type of problem.
So when you say the oceanic deep field, that's due to electrical currents in the ocean?
I'll go into it in more detail. Yeah. But yeah, I guess I like to just start by discussing the signal itself. And as I'm sure most, like everyone here is familiar with, since you're all plasma physicists, right? Any magnetic field you measure, it's going to be the sum of all the different magnetic fields that are superimposed there. So depending on what, like magnetic field, depending on the source of the magnetic field you're interested in, you have different tricks for trying to isolate that field. So even though this is a 2 nanotesla signal in a like 60,000 nanotesla background field, we can take advantage of the frequencies of the ocean's field and also take advantage of the relative location of the source fields. So like if you're using like Gauss decomposition for the potential field, right? You're separating the field into internal sources and external sources. So if you're able to use like both observatory data and satellite data, this can strengthen your ability to look at fields from the ocean. Okay. And so now we'll actually dive into the ocean, and I'll get into exactly what Greg was just asking. So the ocean's magnetic fields come from its electric current, and this is the basically equation that's used to describe the ocean's electric current. I know like in the plasma world, this equation can be much longer and more complicated. And I've had plasma physicists ask me before, like why this is so simple, but it basically just is that all other terms are negligible. And these are the terms that essentially matter. So we have first the seawater's electrical conductivity. And globally, like the average at Earth is 3.31 Siemens per meter. And then the next important term is the velocity of ocean flow. And so this is where things also get interesting, because this means every type of ocean flow is creating its own electric current. And then that is crossed with basically the background magnetic field, which here you can typically just describe using models of Earth's core magnetic field. So we often use the International Geomagnetic Reference Field model or the World Magnetic Model. And then, yeah, this is just a cartoon I made for people who maybe are like less familiar. Yeah. So this is the Earth's main field. We have ocean water. I like made the ions bright yellow, and then, you know, there's electrons that are also there traveling faster than the ions. If the water is going this way, we have the field going that way. It's just right-hand rule for Lorentz force that you get these electric currents forming. And then again, we can use right-hand rule and see the magnetic fields that get induced by that. And I basically am breaking this cartoon down into another cartoon to just fully describe this field. So we'll have a field component that's toroidal, that is basically horizontal within the oceans itself. So if you have observatories in space or like on an island or on the coast, they'll be extremely challenged at observing this toroidal field, because it right, like it spatially decays pretty quickly, like 1/r² past the ocean. And there's only one observatory on Earth that's continuously operating on the seafloor. So this is our only observatory that's continuously able to detect this toroidal field. Instead, most, oh, well, so I guess here I was mostly just, so yeah, you'll have like magnetic field induced with the current, and like most of the ocean flow that's dominant is horizontal, but there also are vertical flows in the ocean as well. So it leads to toroidal and poloidal magnetic field components in the ocean.
Slow down here.
Yeah.
So you started with Lorentz force. So this is magnetic field. So that B, is that the B of the magnetic field? Of
This
the dominant dipole field?
yeah.
Which is roughly vertical, or
Well,
but it's not toroidal, right?
The Earth field, it depends where on Earth you are for which term dominates, but you have both vertical and horizontal components. Like if you're near,
Right,
yeah.
Okay. And then V is vertical, so that creates.
Well, V is, it's both vertical and there's a horizontal, but vertical is much more dominant than the horizontal. And this is like largely why that toroidal field, you have to actually be in the ocean where there might be the vertical velocity to detect it, because it is so much weaker generally.
Them are meridional, in the meridional plane, right? V and B, and so that creates a vector product in the toroidal direction. Right?
Yeah.
And that's balanced. Okay.
Is everyone feeling comfortable, or it? Okay, cool. Yeah, so I guess so then when we're using data from satellites or island observatories, instead, like we're like you're just detecting this poloidal field, which is often just written as like BZ.
You said that there's one observatory on the bottom of the ocean. Is that specifically for this purpose, or is this a?
Yeah, so it's run by one of my colleagues at University of Kyoto. And he set it up in the early 2000s. I mean, yeah, I think for a variety of geomag purposes, but like we've used it to look at fields from tsunamis, which I will discuss later in this too. And yeah, you can use it to look at tides, do any of the things that I'm going to discuss here.
What about regular ships? Do they have magnetometers to some of them?
Sometimes. So in terms of like observations, I don't know if you've heard of like magnetotellurics. This is like a solid earth geophysics method where you set up a magnetometer and then like electrodes to measure electric field, and you use both the magnetic field and electric field to probe the resistivity under you. So they'll do these surveys where they set those up on the seafloor for like a month at a time. So like you can sometimes like ask those people for those data sets. And then NOAA, like in the geomag group at NOAA, they collect all types of geomag data. So there will be like sometimes shipborne magnetometers. When you have a magnetometer that's not secured on the ground of the ocean though, then you're pretty much limited to just using like scalar data because it's just very hard to reliably get the components. Yeah. Okay. So yeah, we'll start with tides. And I found that unless you work on tides, sometimes tides are just never something you think about. So you'll think about the tide as being something you see when you're sitting on the beach at vacation and you see the tide roll in and the tide roll out. So often people be like, wait, why are you saying tides plural and not just one tide? But basically there's a lot of different tidal modes that arise from the different harmonics of like Earth's gravitational interaction with the sun and moon. So if you're looking at a power spectra of magnetic data at an island, you'll actually be able to see all these different tidal modes. And like the longer your data set is, the more you'll be able to see like these long period tides as well. And so for geophysical applications, this is like really interesting and useful because basically having different harmonics, right, like different frequencies of magnetic fields that you can look at, you can use those to probe to different depths within the Earth. And like I said, you just need more data to be able to resolve longer period signals. So at Earth, of all the different types of ocean flow, tides are the flow with the best constrained velocity, like largely because we have a lot of different data sets and ways of describing those. And they can be used to probe Earth's interior. And what I'm showing here is a visualization of the lunar tidal mode that's a little over 12 hours in period. And it's, if you go, hang on, I'll go back to the power spectra for a moment. It's this M2. So it's like the dominant lunar tide within a day, basically. And it also happens to be the first tidal magnetic field to be extracted from satellite data. So it's also the first tidal magnetic field from satellite data to be used to like probe into the Earth. Yeah. And so this process of using tidal magnetic fields, hang on, sorry, I'm trying to change the slide and it's like, okay, here we go. It's just taking advantage of the electromagnetic skin depth concept. So if you have an electromagnetic wave penetrating a material, how deeply it penetrates before diffusing will depend on the period of that wave, as well as on the conductivity of that material. So if you know the period of the wave that you're using, you can then use that to like infer the conductivities of what you're penetrating. And so for geophysicists, I guess like the standard way, like the way that's typically standard for probing into a planet is seismology. I'm not sure how familiar you all might be with seismology, but it's like you're basically just using like earthquakes and acoustic waves from like explosions like an earthquake to probe Earth's bulk structure by looking at like velocity changes in the Earth as the wave propagates. So that gives people like bulk properties, right? Like they can see like, oh, there's a plate subducting here, and then this must be magma because the velocities are attenuating. with electromagnetic sensing, we're instead relying on the diffusion of an electromagnetic wave and the changes in electrical conductivity of that material, which means instead of bulk like properties, we're relating like the temperature, melt content, water content, and composition, since those are all the properties that determine the electrical conductivity. And when we use oceanic magnetic tides, it's pretty powerful because instead of having, just like one seismometer or one magnetometer as an observatory, like when we're using satellite data, it means all of the ocean gets to basically be an observatory. And so this was something colleagues and I did where we used that lunar tide to try to invert for the electrical conductivity of Earth's crust and like upper mantle. And so what I'm showing here is basically our model results, like the thick black line, one's from a sparse model, one's a smooth model, and then the gray area is showing 1,000 models with like top 10% best fitting. And so one of the cool things right away is that we found this sharp change in electrical conductivity that coincides at the same depth where seismologists have determined a boundary between Earth's crust and upper mantle. So this was like, confidence boosting that we're finding the same planetary boundary within Earth as seismic studies. And then
Just trying to, it's a lot of conductivity versus depth, but it's inverted. So it's kind of difficult to process a little bit.
or you
Normally,
used
I
to
would
seeing
put depth
conductivity.
along this line and conductivity would.
I
this
see.
line, but now-
Well, we're doing it depth, like you're going down into the planet.
Yeah, not just the direction of the axis, but the orientation of the two axes. I would plot conductivity as a function of depth. That would be more natural to me, more easier to understand. So what do you say? So which one is more conductive? Deeper?
Yeah, so the deeper you go, it's more electrically conductive.
Okay.
And then like we put these two lines here that are from like geochemical experiments of like what the electrical conductivity at depth would be for like dry olivine. So this is a type of mineral that the mantle is supposed to mostly be composed of versus water saturated olivine. And so our point here is just the better we can like refine this electrical conductivity with depth profile, the like better our chances of answering this like big ongoing question of how much water is actually in Earth's mantle, which has implications for both like geophysical processes as well as the formation of Earth.
So you're suggesting that there's water in the mantle down to 300 kilometers or something like that?
Yeah. Which, no, I think,
We are not geophysicists.
yeah, that's something that I think isn't necessarily surprising, but it's something that, I mean, you can see the spread here, right? Like, it's an ongoing challenge in geophysics to quantify how much water is in the mantle, because that answer really changes, like, I guess, implications for Earth's history and how plate tectonics works and things like that.
Also for those of us who are
Yeah, I'm like not a big geology buff either. It's just it's the most common mineral for the mantle. It's like all we need.
Iron mineral?
I think so. But, oh man, like some geologists, they took so long ago. The prof would be like, "Why did you forget?" But yeah. Okay, so yeah, like this notion of using tidal magnetic signals to probe into a planet is also something that's one of the inspirations behind like the Europa Clipper mission, for instance. So hang on, what do I have here? So we have similar physics, right? Like there could be a salty ocean under Europa's ice shell. And Europa's has a changing background magnetic field since it's traveling through Jupiter's magnetosphere. There are two different types of magnetic tides that can be considered here, because like when I was talking about Earth, right, the tides I was talking about are gravitational tides happening on the ocean, right? So we have that at Europa as well. I just don't know that there's reliable tidal models of that. Like I mean, there definitely aren't compared to Earth. But then we also can just say at Europa, we have basically magnetic harmonics or dominant magnetic periods from Europa's orbit through Jupiter's magnetosphere. So these are not necessarily going to be the same periods, I think, but for electromagnetic sensing purposes, we can use these magnetic tides.
Oh, sorry, before you go on, are you switching from Earth to Europa? No.
Yeah, just for a little discussion.
Or just a little discussion, because I had a question about the Earth. But maybe I'll ask it later.
Whatever you want.
I didn't have to question about Europa. How do we know the tides?
These dominant these.
Yeah, is it theoretical? Or is it, I mean, are we modeling them?
Yeah, this
based on
study that
gravity and various periods?
well, so what I'm saying here is we don't necessarily, like, I don't know of studies of like the gravitational tides, but this study was using different magnetic field data and like known properties of Jupiter's magnetosphere and Europa's orbit to be able to model like,
This is using magnetic sensing.
yeah, from Galileo to basically say what will be dominant magnetic signals if you like were to have like a power spectra of magnetic field data at Europa. So then I'm being
Is Europa locked in its rotation with its orbital rotation? I mean, does it have?
I think so. I'm like, hang on, Fran.
Absolutely, absolutely.
Yeah.
So everybody has to remember Io, Europa, and Ganymede are in a 4:2:1 resonance, which is extremely powerful in terms of the tidal locking, and they're all in phase locked, facing the same direction towards Jupiter. So you can imagine that results in extremely high tides, a lot of power in the tides, which
Well, there's
You know about-
some changes in the orbit's obliquity, right, Fran? And like that's part of why it can have extreme tides.
Sorry, but so the day on Europa is it equal to its year around Jupiter, right?
a day is its orbital period around. Yes.
Yeah.
Right.
Yeah.
So why are there any tides at all? Or are they caused by other moons?
Well, so there's the interaction with Jupiter, but there's also the interaction with the other moons. So Europa goes around once,
Right.
then Io goes around twice. So there's the Io Europa involvement, and then Europa goes around twice for every once that Ganymede goes around. So you can see with these three moons tidally locked into each other, and with Jupiter 310 times the mass of the Earth, these are really strong gravitational tidal forces that are happening.
Yeah.
Thank you.
And this is like,
Yeah.
right, why it's believed like tidal heating is keeping an ocean active.
Right.
Yeah.
Thank you.
So that's sort of getting to the point of this first bullet. Like there definitely are physical oceanic tides happening at Europa, but the tides, or I shouldn't say tides, the magnetic like periods of interest or the magnetic harmonics that we're interested in are more just caused, yeah, by like Europa's passage through Jupiter's magnetosphere. So this is separate from those physical tides.
Why would that cause any signal? Isn't the Jupiter magnetic field that roughly axially symmetric? And what does it change?
It changes.
It's
And, like-
tilted by 10 degrees. And so you get, and that's stuck with Jupiter's 10-hour rotation period. And so each of these moons is a dB/dt due to this field oscillating up and down.
So the field oscillates because Jupiter's magnetic axis is
It's tilted.
Tilted, yeah.
Yeah. Thanks, Fran.
Sorry, just for- sorry.
No, this is good.
Yes, I do remember indeed that Jupiter's spin period is about 10 hours. What are the spin
Yeah.
periods of, let's say, Europa?
here.
What is it?
So Io is 42 hours. So that means that Europa is 84.
These
Well, that
dominant
means-
peaks, this one is Europa around, like it's Jupiter's magnetosphere.
Oh, I see.
This one's Europa's like
Oh, okay.
day.
Right.
Yeah.
Okay, I'll shut up.
No, thank you, Fran. I generally have a much more Earth-focused audience, so the Europa questions have generally been like so general. I haven't had to like remember details.
Oh, just some basic,
Yeah, just basic parameters. Yeah. But yeah, so with Clipper, there's interest to try to use these dominant magnetic periods to also do like electromagnetic sensing at Europa. But yeah, so I just sort of walked you through these major difference in what type of tides we have at Europa. And then with the Clipper mission, a major difference there is also that this mission would be a series of flybys. So it's different than like low Earth orbit satellites that are just always orbiting Earth, giving you continuous data. Here it would be like 50 flybys. And one of the big questions then would be like, how many flybys do you need before you're able to like piece that data together and use it like in a reliable way towards this method? And then this is just a cartoon I drew of Europa's magnetic system, basically. So Europa's in this background field from Jupiter's magnetosphere. There's evidence that there's a tenuous atmosphere and ionosphere at Europa. There's a ice shell, possible ocean layer, and then how well differentiated Europa is still also quite ambiguous. But there's, you know, some studies that say no core field, as others that say there might be a core field. So many aspects of the system are pretty unknown. And so like using both plasma data and magnetic field data from Clipper will be really important for like filling out this picture so that those magnetic harmonics can be used for EM sensing. Because right, like if you're not taking into account like external fields and you're just assuming the entire signal you're observing is from the ocean, then you're going to be off in your geophysical estimates. Yeah, and EAST is also going to be sending the JUICE mission out to the Galilean moons. So it's going to insert orbital insertion to Jupiter in 2031, and then it'll be doing flybys of all the Galilean moons before orbiting Ganymede for a solid year. So that will also be really interesting.
Sorry, and Clipper was NASA? Or?
NASA, yeah.
NASA.
And it should be arriving same
Same time,
timeline.
right.
Yeah, which is cool.
So they will collide.
Wide, hopefully not. And then in this like recently released decadal survey, a lot of interest is shifting towards Enceladus, which is a moon of Saturn that's been observed to have these like plumes shooting out of it. So it's the moon that most definitively has like liquid water, since it's shooting out plumes. So whatever mission happens there, I'm definitely hoping like magnetic field and plasma instruments will be included so we can figure out probing the inside of Enceladus. Yeah, so like because it travels within Saturn's magnetosphere, I'm just like presumably it's also encountering time-changing background magnetic fields, which would then make this possible. And then just to sort of wrap up the title section, I'm like, there's a lot of candidates of ocean worlds in our solar system. And so for any of these, we would need to figure out like what sort of mission will provide reliable data, enable like separating out internal and external magnetic fields. And then once you're able to do that, you could do electromagnetic sensing using dominant magnetic periods or tides. So yeah, the summary page. Oh, sorry.
No, just want to say very cool and interesting.
Yeah, there's like a lot of variety of possibilities.
So Callisto is the fourth one?
Yeah, well, I think it's Io. Yeah, and Ganymede's the largest.
Right.
Yeah.
Callisto is not much smaller though, right?
I don't think so.
If it's to scale, I hope.
I'm like, just, yeah. And I mean, the Earth here was just separately stuck on by me. So the Earth part is not to scale. Yeah. So yeah, so using no, because I think, isn't Ganymede comparable to the moon, Fran?
No. Ganymede's the largest moon in the solar system. So Europa and Io are about the size of the moon.
Oh, okay.
Ganymede's bigger, as is Callisto, but Callisto's denser. It's got more rock, and it's not in any tidal resonance.
So in summary, oceanic magnetic tides are just basically magnetic signals at discrete periods and frequencies, and they can provide global coverage for probing into a planet at different depths. You can obtain information on the interior electrical conductivity, which then relates to temperature and chemical composition. And these results then, like at Earth, have been shown to be consistent with seismology while also providing new information. And so for planetary missions, this can help us to either confirm the detection of oceans or to constrain the interior structure. Okay, and so now we'll shift gears a bit to going to a longer period signal of circulation. So here,
Actually, sorry, before you do that, there's a question on Zoom.
oh yeah,
Can you say a general statement like on Earth, when there are higher tides, the magnetic field from the ocean is stronger, or is it just much more complicated than that?
like, so it depends on just like that equation that I showed you. So I think like whether or not it depends with like water height actually being high probably depends on just where you are. But if you're always trying to like plot like the magnetic field data and like the water data, I think you would be able to correlate that.
But essentially, it's really the water flows.
Yeah.
It's the water flow, like the background magnetic field, and then the local like salinity that can make the biggest difference. So
Well, that can vary.
yeah.
Actually,
At the end, or maybe I can just
well, the
quickly.
magnetic field is roughly static. So in terms of time period, to address Greg's question, so one would think that, okay, when the velocity is highest, right, V cross B is highest, the magnetic field is largest, strongest, right? But then you said salinity.
So
It's still,
yeah, it'll depend on the electrical conductivity and the velocity and the main field. So like, for instance, if we look here in the North Atlantic, that area, and then when New Zealand pops up, like that area too, they're kind of close to the magnetic poles. So those areas tend to have strong tidal magnetic signals. And then there'll be some continental shelf areas where like basically the depth integrated electrical conductivity there is much stronger than like in the open ocean. So you can sometimes see like more of almost like a coastal effect in the tidal magnetic field strength.
Sort of permanent effects, I guess. The question is, if you're sitting at a given location, doesn't
Yeah.
matter, it's just some location, and you're observing this perturbed magnetic field varying up and down. Is it highest at periods of high tide or low tide, right, or something like this? I guess it's just so at the given location, the magnetic field of the Earth is fixed. Maybe salinity is fixed. Right?
Well, yeah, and I guess I'm saying like,
the thing that changes is the velocity of the fluid.
yeah. So I don't know how, like, if you just correlated the water height and the magnetic field height, like if the correlate, like if they would just go up, like it might depend on the tidal mode. Yeah.
Before we move on, I also have a sort of general question.
Yeah.
So you gave us the value of the resistivity or conductivity, right? In some units that I'm not familiar.
For the seawater?
Yeah, for the seawater, right? And well, the units, I mean, these values don't tell me anything. Do you know what are the corresponding like magnetic resonance number?
No, sorry.
That's how important it is.
Hang on, I'm just gonna make a note to self. Yeah.
For different velocity.
Yeah, I don't know what that would be.
So we just, some characteristic scale times characteristic velocity divided by the resistivity.
But for like, if you're getting at basically how important is this component for the magnetic field that you observe, in our like just sort of simulation work, it can like add up to like 10% error. So a lot of times, depending on what study we're doing, instead of using a global mean, we'll try to use like a 1 degree grid of like conductivity values.
I just wanted to get an overall feeling of how big this is. in like dimensionless, relevant physical dimensionless quantities like the magnetic resonance number. I guess it's a small, right? It's small. In plasmas, we usually deal with very large magnetic resonance numbers,
Yeah.
highly conducting fluids.
And in
This is-
marine EM, no one ever like writes things in magnetic Reynolds numbers. So like I know what you're talking about from reading like dynamo and like plasma work,
Yeah,
but I'm just like,
exactly.
I've never thought to try to like use
just-
those sort of semantics for
But
this.
just to get,
Yeah.
whether it's large or small. I guess it must be small.
Yeah, so I'll try to
Okay,
Sort of
I think,
give you guys the right points. I love, yeah, this has been a fun discussion. But yeah, so for circulation, ocean, this is just an overview. Oh, sorry, it's like blurry on that screen of major currents. And the main takeaway here is that ocean circulation, like you have dominant currents at the surface that are driven by wind. And you basically have these big gyres. But the overall, like not just the top of the ocean, but the entire ocean, that whole circulation conveyor belt, it's buoyancy driven and it depends on changes in temperature and salinity. And to like have water that's, you know, like at the top of the Atlantic right now, eventually like go through the whole conveyor belt and be back there takes hundreds of years. So these surface horizontal currents are much faster than like those vertical currents that drive the whole system. But for like oceanographers and climate scientists, like they care about all of it. Yeah. So if we look at the magnetic fields, on the right here, I have the magnetic fields from that lunar tide. So you can, and this is all supposed to be at satellite, like 450 kilometers altitude. So you can see that this reaches like peak values at like 2 nanoteslas. For ocean circulation, I had to have the scale for you to be able to really see anything worthwhile. So it's basically under 1 nanotesla at satellite altitude, and the only currents that produce magnetic fields that have a chance of being detected at satellite height are from that Antarctic circumpolar current. So that's the only current in the world that just gets to go around all longitudes. So it's the fastest, like strongest current.
Did you say the tidal flows are mostly vertical? And then these circulations, they'd be horizontal relative to the,
Yeah, you could say that like tides are, the dominant velocity is vertical. For circulation, you have horizontal velocities that do dominate, but like when you're looking at the full time scale of it, there are also vertical velocities. They just are so slow. Yeah. And so what's kind of cool is NOAA, the National Oceanic and Atmospheric Administration, and the Strait of Florida, they have these 100-kilometer long voltage cables that were like originally put down for telecommunication purposes, but now they just are past like, well, not now, since like 1985, they've been passively recording the electric field across this strait. And this data actually correlates really well with the ocean transport going across the cable. So for over 30 years, NOAA's been able to produce daily transport values and monthly transport using this electric field data. And so like doing my PhD, I was like, well, that's cool. Like, could we do that on a really big scale? Like there's a lot of different passive voltage cables that were put down by like AT&T decades ago. And so we were able to get some data going from California to Hawaii and also from Japan to an island that's in the Kuroshio Current. And what I'm showing you here in the background is meridional transport. So this is one component of ocean flow, integrated ocean flow, basically. So you can just sort of see like this is the area with stronger or like larger currents. This area, that surface gyre, is just so much more diffuse and slower. So just going into this, it's like you already would expect trying to use these cables to look at transport to maybe be more challenging. Here where the cable's so long, so it could have eddies going in multiple directions, right? Because the voltage you look at, it basically, it depends on the integrated transport, right? And here the velocities are larger, but that ideal setup that like NOAA had at the Strait of Florida, it's when you have your cable perpendicular to the current. So it's not an ideal setup, but I wanted to just see how it would look. And so basically what we have here is in blue is our model, like trying to predict what signal we would expect. And then in red is data from that cable fit to monthly splines, and then green is seasonal splines. So generally what I say is the takeaway here is it's reasonable, like we can say that maybe this could work, except it's definitely not actually practical for physical oceanographic purposes, right? Like at least they're on the same scale and maybe overall have the same ups and downs. But the level of correlation is much lower than in that 100-kilometer Strait of Florida cable. And when we look at the cables going between Hawaii and California, it's like slightly worse, right? There's a more disagreement, but overall, just I'd say the same takeaway where the fit maybe encourages trying to do this in the future, but it's not practical, especially not with these cables. And so just this section sort of ends with like a pipe dream of just like, what if we were able to choose where we put passive voltage cables? So what if we put them in key locations in the Antarctic circumpolar current and try to measure the transport of that current? So yeah, for this section, it just, yes, we can use electromagnetic methods to monitor ocean circulation, but it's only reliable in really local scales with ground-based data. More work would need to be done for it to happen on a basin-wide monitoring. And so far, it's basically just impossible with satellite magnetic field data because the signals that you're trying to search for is just too small and the period is so long.
What are the obstacles to do this?
The satellite?
Laying down the cable between
Oh,
Argentina and Antarctica. Is it just funding?
yeah. I mean, I don't know if anyone's proposed it, so I'm like, wait, one day it might be a dream. I don't know.
The station on each side and put the cable, right?
Well, and I think like for at least like the end of Argentina and Antarctica, I think there already are research stations on each side doing other type of like studies. So
I was imagining like an amateur Morse code enthusiast club full of like really rich billionaires.
if I became friends with Jeff Bezos, anything could be possible. Yeah. Yeah. So if we think about icy moons, like it would be extremely challenging to try to constrain ocean circulation, right? If it's already this hard at the most well-observed planet in our solar system. But it's interesting to think about like what it might take in the future. And I guess I'll just sort of end here, like in my notes, I like to point out that I have some colleagues at GFZ Potsdam who try to approach studying ocean circulation using EM data, not by trying to look at circulation signals directly, but by actually trying to look at changes in tidal signals and use those changes to try to figure out how like the salinity or temperature of the ocean is changing. Okay. And so now it will come down to the smallest period section of tsunamis.
Yeah. Like I understand that there are these large bulk circulating currents.
Yeah.
But for an electrical current, why would that arise if the whole fluid is moving together? Like because you have positive and negative charge moving together.
Well, so that the net like electrons and ions are not perfectly traveling together is pretty much the answer.
Okay.
So like electrons will always be traveling faster than the ions, and the ions are maybe a bit more, I guess, like far behind. But
This is fluid, conductive fluid traveling past the magnetic field.
yeah.
So there is an electric field induced in the meridional direction, I guess.
Yeah.
To drive the meridional current, electric current.
Yeah. Okay, cool.
Uh,
Yeah, so
And also, so before tsunamis, so going back to Europa, are you going to come back to it or not?
you can go ahead and ask.
What do you actually maybe not know, but think are the physical conditions in that ocean?
Wait, what are you asking?
What do we think are the physical conditions
Oh, like
in that ocean, like size, temperature, anything else?
for all of this, it's basically like there's a wide range of possible parameter space.
What is the range?
depending on, I guess, what study, like the ocean could be tens of kilometers to hundreds of kilometers. The salinity range, there can also be a wide range. I don't
And
remember.
but it's liquid water, right?
Yeah, it is liquid water.
So it's between.
But there are people, I guess, who do debate like how slushy it might be. But yeah, and
So it's between like somewhere between 0 degrees and 100 degrees centigrade.
yeah, but I think it's closer to 0. Yeah. But I think, I don't know, Fran, you're welcome to interject here if you have some like geodynamic study in mind.
So,
with-
I mean, it's not a huge range. I mean, there is a range. There is some induction measurement signatures that are measured, but it's not a unique. And I think that the big issue is conductivity, depth, anti-correlation, say. And so you could have a shallow, highly conductive, or a low conductivity deep, or something like that. And so that's not very well constrained. Similarly, the temperature is not tightly constrained, and who knows whether or not there's material volcanic eruptions that are putting minerals in from below. And so everybody's sort of speculating about these things. There's some, it's not completely open. I mean, we do know that there is a conducting region, ocean in there. It has to be an ocean, not ice, because of the conductivity. But that's why we're sending a spacecraft to go measure these induction signatures.
And like, I think when you're able to pair the EM data with like all the other instruments Clipper will have, that'll help further, keep adding constraints to the problem.
Right.
What are the expectations in the research community of what, let's say, Clipper or JUICE, I guess?
Yeah.
What will they be able to do regarding like establishing the properties of the ocean?
Well, definitely establishing like the structure, like how thick the ice shell is, how thick the ocean is, how differentiated. Yeah, for sure. Like one-dimensional knowledge, I think everyone agrees that will be able to happen. Yeah.
Two-dimensional, because they'll be mapping. They have multiple flybys. I'm on the science review board, so I've sort of have been following what Clipper's been doing. And so they're going to be measuring, is there any liquid water anywhere near the surface? Are they going to be measuring, are there sort of cracks in the ice? Is material that comes out from the ocean onto the surface? What is that brown stuff on the surface? What is the depth of the ocean, the conductivity of the ocean? What is the interaction of the plasma with the ice and the atmosphere, sputtering of the surface? What's the plasma interaction with, the limited atmosphere there? All of these things, they'll be able to be making lots of measurements.
Yeah.
So sounds like an exciting mission.
Yeah. Cool. Thanks, Fran.
And of course, the most important instrument is the University of Colorado dust detector that will measure whether or not there's stuff coming out, sputtered off the surface, and they'll be able to measure these small little dust particles of ice and measure its composition. So that'll be very important to get some sense of the, what's coming from deep inside out onto the surface and sputtered and knocked off the surface.
I thought someone had a hand.
I just I'm a little confused about, because you've been talking about how the ocean currents on Earth are really weak. Like the magnetic field is really weak and it can't be observed by satellite. But
For circulation.
first, okay,
Yeah.
but like even for like an overall weak field caused by tides, that's fairly weak.
Those the 2 nanoteslas.
Right, but so then why do we expect we can measure Europa's oceanic magnetic field
Well,
with satellite?
for part of it is because we already seem to have done that from Galileo data. But it also is just overall a totally different like magnetic system, right? So on Earth, the core field is 60,000 nanoteslas. At Europa, there's debate of whether there even is a core field, and if there is, people were speculating it doesn't exceed 20 nanoteslas. Meanwhile, the induced signal can reach 100 nanoteslas. So like what your dominant like magnetic fields are at Europa is different. And like the background field here too
And why is the
is weaker
field higher
at Europa.
than, yeah, than the Earth?
Mostly. But relative to the core field,
Right, I understand
Yeah.
also the core field, but I'm just wondering, just in general, why is it?
Well,
higher? Because you have
Induced due to oceans or just
Yeah, just
due to
due to
motion?
the oceans.
No, but there is also just the main field due to the motion of Europa itself or Jupiter's.
Yeah, so I guess part like
Is it
there is like the way current studies like looking at induced dipole from Galileo, they're basically just looking at an induced internal dipole and not how do I say this? Like it seems like there has to be a conductive layer causing that, but it could be coming from other sources. But like I get what you're asking.
Yeah,
I don't know,
just
that might
thinking
be
about-
something we need to learn from
I'm just
Europa.
thinking about, like, J is equal to depress the equation, and, like, I'm wondering, is like Jupiter's magnetic field stronger than like the Earth's dipole at these locations, or could there be more solidity? Just, I was wondering, you know, if that's maybe what's causing a slightly stronger field, but I also understand like the background to noise ratio is.
Yeah, and also we're not exactly comparing apples to apples here, I guess, when we say like the induced field at Europa, and then I say like 2 nanoteslas at Earth, because the 2 nanoteslas at Earth is for one specific like tidal harmonic.
Okay.
At Earth, it just would be extremely hard to try to say like this is the entire ocean induced field.
And my other question, I mean, I don't know if you talk about it at the end, but just other kind of applications for measuring the Earth's magnetic field, besides, because I know you talked about like measuring like where that layer is in the under the Earth's surface, but are there other applications to knowing what this field is?
Well, it's pretty much to study like from tides, it's pretty much to study the interior of the Earth and then the ocean itself. So like I was saying, like colleagues at GFZ Potsdam who like have more of a traditional oceanography background, or they've been doing a lot of modeling to see like if you include tidal magnetic signals in oceanic data assimilation models, like will that improve your predictions for like oceanic temperature and salinity? And so far they find that it does, which is pretty cool. Also, like, how much wiggle room is there on time? Like,
I really want to hear about it.
okay, cool. Because I'm like, you guys are so curious. That's great. So yeah, so tsunamis, right now we're coming down to a flow that has a period of like often just 10 to 20 minutes. And I like to start with this, hang on, this cartoon of the tsunami flow. So it's the same equation, but you can think of it as you have this epicenter, like the earthquake, or in the case of Hunga Tonga, a huge eruption. And from there, you have the tsunami wave front propagating out from that epicenter. So you have the flow going out this way, main field this way, and you wind up having an electric current that just travels along this wave front. All good, cool. And so main motivation for studying tsunami magnetic fields, because most of the papers within this field are honestly from like the last 15 years. And a lot of like, there's been especially like an explosion in papers since the 2011 Tohoku tsunami, because that was just such a huge event. And like a lot of people were able to detect magnetic signals from that tsunami. And there also is, of course, just the humanitarian point of view, right? Like there was just a lot of towns on the coast of Japan only had like 8 minutes of warning for the tsunami. And this nuclear power plant, like the what ifs, right? Like what if they had been able to turn things off better? Like would more warning time have made a difference? So a lot of Japanese scientists study this event, and then I also did. But if you give a little background here, the scientist I worked with at NOAA, he did one of the first observations of successfully like isolating a magnetic field for a tsunami, and it was for the 2010 Chilean tsunami resulting from a magnitude 8.8 earthquake. So that's a really big earthquake. Tohoku was a magnitude 9.0. And
How did you do that observation? Was that space-based?
Oh, no, sorry. All of this is going to be ground-based. Yeah, this will all be ground-based. And so one of the things that's really been, I guess, like in the last 7 years, exciting this field is that the tsunami magnetic field doesn't need to arrive with the water wave, that sometimes it can actually arrive before the water wave, and depending on the event in the observatory, this could be by as much as 4 to 20 minutes. And so the examples I'm showing you here are both for the 2011 Tohoku tsunami. So first, Tata and colleagues, like this is comparing the water levels at Shishijima Island, which is like a Japanese island off from Japan. And so this triangle is showing when the tsunami water wave reached this island. Meanwhile, the magnetic field actually reached that island 20 minutes before the water wave. And part of this is that the observatories at this island have a bit of a unique setup where they're kind of like in a bay. So like it makes sense on the one hand for a magnetic field to just arrive maybe before the like water might get into that bay to begin with. But Takudo Minami and I like, so he does a lot of modeling of tsunami electromagnetic fields. And in 2015, around the same time these observations first coming, he found that like you can have dispersion in the tsunami magnetic signals, and it'll depend on like what part of the ocean the tsunami is traveling in, basically like the depth of the ocean. And then I did an analysis where I was breaking down the tsunami magnetic signal, looking at the different period components, and was able to like basically confirm that dispersion is what's driving this, because it's the longer period components of the magnetic signal that are arriving before the like shorter period signals, and those are more likely to be arriving with the water wave. And then since then, we've been like, this was like sort of the catchy title that like tsunamis can have primary and secondary arrivals like seismic waves. But really like what we're saying here is that the horizontal component of the tsunami magnetic field is actually significant. Like it actually can be detected, even though like the horizontal flow of a tsunami is obviously like much more dominant than any vertical flow. Vertical flow still matters enough. And this is kind of a big deal because this gets to something you were asking much earlier on, right? Like Earth's main magnetic field depends on where you are on Earth. And if we only look at the vertical component of Earth's main field, at the magnetic equator, it's 0. So like within this community, there was a lot of concern, like, can you actually use tsunami magnetic fields for warning systems? If, you know, a tsunami is happening along the magnetic equator, that means you're doing a cross product with 0. You're not going to get a signal. But then what we found is, well, like the horizontal component is much smaller, but it still matters. So when you're at the magnetic equator, you will at least see that, even if you're not seeing this larger peak from the vertical field.
There's a question on Zoom about whether there's any difficulty distinguishing magnetic field due to the tsunami water wave versus some rearrangement due to the earthquake itself in the cross storm.
Oh, so that isn't from tsunami magnetic fields from the ocean versus like in the solid earth. Like the ocean field is always, I think, going to be much more dominant. What I thought you were going to ask is what the real like challenge is, which is separating the tsunami magnetic signal from what might be happening in near Earth space. Because there's like low frequency waves in the magnetosphere that have a similar period range as tsunamis. So if there's any kind of space weather happening, then you need to get real clever and maybe lucky in your data processing to like know you're pulling out tsunami signals instead of just magnetospheric signals coincident with the tsunami. Yeah.
The goal is to have not predicted, but earlier warning capability.
Yeah.
It's actually practical.
Yeah, there's an actual practical goal. And then I think maybe the more short-term practical goal is because you can relate the magnetic field from a tsunami to the tsunami's vector velocity field. You can use that to improve like geophysical source models of how that tsunami was created, which is like helps understand like the earthquake's rupture, or like in the case of Hunga Tonga, like what happened with that eruption. So this is shifting gears a little, but I looked at this event last year, so I just like to add this in. But basically at the start of 2022, this submarine volcano had like a huge explosion. That's one of the biggest measured, or maybe the biggest measured explosion in humanity. And I was curious, like if I pull data from a lot of Pacific Island and coastal observatories, like can we see clear magnetic signals from this event? Okay, I didn't include that. And one of the things here, so like this led to both a water tsunami, like a classic tsunami in the ocean, but it also led to really strong acoustic waves that propagated through the atmosphere and into the ionosphere. So along with seeing like a tsunami in the ocean water, there was also what's called a meteo tsunami. So this is an atmospheric pressure driven deformation of the sea surface. And then there's also just going to be waves in the ionosphere. So this star is where the eruption happened. And then these are just showing some of the different like Oceana stations I used. And then red is the observatory where we feel very confident that those signals were due to the eruption. And then you'll notice I also use this observatory that's in the middle of the Australian desert. And this is there because what I was saying earlier about possible like noise from the magnetosphere. So one of the ways we try to like remove noise and be more certain we're looking at local signals is to just include some like continental observatory where then the only like magnetic signals that these multiple stations would have in common would be like larger background external signals, and then use that for noise removal. And so these come on scene. So at this Western Samoa Observatory, we found these really high frequency signals. They're like 3 to 5 minute period. So that's much higher than anything that's ever been observed for a tsunami. And sort of in the past year, there's been studies coming out that are saying like that this is probably a type of atmospheric wave like resonating between the ground and the ionosphere. And so these are actually ionospheric signals. But then with these observatories, like there's clear magnetic signal that I'm like, maybe this is something happening that like it looks like some wavefront that could be moving through, but this is like I just am looking at what happened, and like we're still doing ongoing work to try to see like what in the ionosphere this might relate to, because it's definitely not from the ocean. And then if we sort of move east in the Pacific, at Easter Island, we saw these like 90-minute signals coincident with the arrival of like tsunami waves from the eruption. But 90-minute period is much longer than any sort of like normal period range for a tsunami. So again, we're suspecting this might actually be acoustic waves in the atmosphere or different processes happening there. Yeah, it's 90 minutes. Okay, and then this is Shishijima. So this is the island observatory that I mentioned before for the Tahaku tsunami. And what you see here, so this is just looking at the sea surface, like the water height variation. So this is before anything gets there. And then we first see this arrival, and that's the meteo tsunami. So that's like wave deformation from atmospheric waves. And then we actually have the classic like tsunami arrival. If we look at magnetic field data, so sorry, this is for each of these observatories. This top row is Shishijima. It was a pretty busy day in terms of magnetic signals at Japan, but there were stronger signals coinciding with when the tsunami water wave reached that station. So right now we're still sort of working on fully separating these signals out and trying to constrain just using like physics-based models, like what is from the water tsunami versus what's from the atmospheric waves that were happening. Yeah. Okay.
There's a lot of wave height variation like that. I mean, to me, that looks like a bunch of tsunamis like happening back to back. Is that what a tsunami looks like?
Oh yeah,
Am I
it's
associating those with like a crest of a wave coming.
And it should be 30
Yeah.
meters high, right? Not 1 meter. I'm just kidding.
no, here I think this the
I mean,
tsunami
nobody-
was 1 meter, like
Oh,
at this tide gauge. I don't know what it would be if we were looking at like the Tohoku tsunami. Um, but yeah, it's
So it's a tsunami.
I think it's just like this, yeah, wave comes out with different wave fronts and then it eventually like dissipates.
Okay.
Yeah. Okay. So summary for this section is just that you can use magnetic field data to estimate the tsunami velocity. You can also use it, like if you were to only have magnetic field data and not that water height variation data, you could use it to estimate the water height variation data. So people want to use this to improve tsunami source models. And then the main like dream is to try to improve tsunami predictions and increase warning time. And there are no known extraterrestrial tsunami hazard applications yet. So yeah, thanks for being in this seminar and having such great discussion questions and conversation.
Thank you.